Hello, my name is Ty, and this is my talk on Coresets for multiple LP regression at ICML 2024, and this is based on joint work with David Woodruff. In this work, we study the LP linear regression problem, where our input is a design matrix A, which consists of n examples and d features, as well as a target vector B, which contains n labels. And our goal is to approximately minimize the objective function, which is given by ax minus b in the LP norm, ranging over all d-dimensional vectors x. Now, for p equals 2, this corresponds to the usual least squares linear regression problem. But for other values of p, we also recover some interesting other problems, such as least absolute deviations regression for p equals 1, and Chebyshev regression for p equals infinity. And here the idea is that by tweaking the value of p, we can interpolate between different behaviors of these loss functions, ranging from average case error for p equals 1 all the way to worst case error for p equals infinity. Now, we're also interested in studying coresets in this work, which is basically just a small weighted subset of the data set. And here the idea is that we want this weighted subset to serve as a good compression or approximation of this original data set. Now, specifically for the case of LP regression, we want this weighted subset such that if I look at the weighted cost, the weighted LP regression cost on the subset, then this is going to approximate the original LP regression cost up to a factor of 1 plus epsilon for some small constant epsilon. And this should be true simultaneously for every d-dimensional vector x. So basically, we just want to approximate this original objective function for every domain value using just the subset. Now, furthermore, we want this subset to be as small as possible so that we get a good compression. Now, if we're interested in single response LP regression, then we actually know how to compute these coresets nearly optimally. So by using a technique called LP Lewis weight sampling, we can actually guarantee that we can always find a coreset of size at most s for any data set, where s is a polynomial that depends only on the accuracy parameter epsilon and the number of features d. So the question that we consider in this work is what happens to this picture if we consider having multiple responses? So now, instead of having just a single response for each training example, we're now going to have m responses that we simultaneously want to fit. And these n responses are going to be specified by this n by m matrix given by capital B. And for the coreset, what we want this coreset to satisfy is to approximate this multiple LP regression cost, which is now the entry-wise LP norm of this matrix, ax minus b, which is now an n by m matrix. And this ranges over all d by m matrices x. Now, it turns out that it's fairly simple to obtain a bound on S, which depends linearly on M, which is the number of responses. And the challenge that we consider in this work is to achieve a bound which is independent of M. So the main result that we give in this work is a nearly optimal bound on the size of a coreset for multiple LP regression. And we show that this size is at most a polynomial of 1 over epsilon and d. And in particular, it's completely independent of M. And furthermore, we can construct such a coreset using this same technique of Lewis weight sampling. Now, in terms of techniques, our main technique is actually going to be a generalization of prior techniques for a problem called active LP linear regression. So in the active LP linear regression setting, the goal is to approximate the solution to LP regression by using as few entries of this label vector B as possible. And it turns out that we can generalize this machinery to work in the setting of multiple LP regression, which allows us to almost remove the dependence on the number of responses M. Now, there's still going to be a polylogarithmic dependence on M if we just kind of use this kind of idea naively. And so we also introduce another averaging type of argument, which will allow us to completely remove the dependence on M. Now, the thing about this result is that this requirement to preserve this objective function value at every d by m matrix x is quite restrictive. And oftentimes, you actually don't need this complete power. So oftentimes, you're only interested in an approximate minimizer. And so then there's a question of whether you can do better if you only want to recover an approximate minimizer. So we also prove a result in this setting, which is called a weak coreset. And we show that if you only care about having this 1 plus epsilon approximate minimizer, then we can improve these previous bounds by a factor of epsilon. And these bounds, again, are almost, they're nearly optimal. And furthermore, we can actually also do this even if we consider an additional embedding matrix, G, which multiplies this AX matrix on the right. And it turns out that handling this situation is actually going to be necessary for some applications that we'll discuss next. So as a result of our results on multiple LP regression, we give two applications. The first application is going to be for a problem called Euclidean power means, and the second application for a problem called LP subspace approximation. So in the Euclidean power means problem, our input is n points in d dimensions. And our goal is to approximately compute a center C such that if I look at the Euclidean distances of all these points to C, and then if I look at the LP norm of these distances, then this cost is going to be approximately minimized. Now, in the sublinear algorithm setting, we work in a setting where n is so large that we can't actually afford to look at all n of these points. And so the way that we're going to solve this without looking at all the points is to take a uniform sample, a small uniform sample of points. So the question is, how many uniform samples do we need in order to compute a 1 plus epsilon approximate Euclidean power mean? So using our techniques for multiple LP regression, we're actually able to get a nearly optimal bound on this problem. And so we show this result, which states that we always need at most S uniform samples. And the bound that we get on S is actually nearly optimal for any sublinear algorithm. And in particular, this resolves an open question of Cohen-Haddad-Solopik-Schwiegerson, which introduced this problem of sublinear Euclidean power means. The connection to multiple LP regression is given by thinking of this B matrix, which is the response matrix on this LP regression problem, as these original input points, and also thinking about this design matrix in the regression problem as the all-ones vector. So if you set up this problem this way, then you approximately are able to solve this problem up to a discrepancy between these Euclidean distances and the LP distances, which is considered in the regression problem. And so the way that we fix this problem is by using a result of Dvoretsky, which allows us to embed the L2 norm into the LP norm. And this is basically the reason why we need to consider this embedding matrix in our result for weak Coresets. So the second problem that we consider is LP subspace approximation, where again, we have n points in d dimensions as an input. And this time we want to approximate this data set by a k-dimensional subspace. So the cost function that we're going to consider is similar to the previous setting. We're going to look at the Euclidean distances of these points to this subspace. And then we're going to look at the LP norm of these distances. So this is the cost that we're interested in minimizing. And in the setting of spanning Coresets, this is slightly different from the notion of Coresets that we considered previously. And for spanning Coresets, we're interested in finding a small subset of these input points, which approximately spans a nearly optimal solution. So using our techniques for multiple LP regression, we're actually able to get a nearly optimal bound on this problem of computing spanning Coresets as well for the range of P strictly between 1 and 2. And we show that 1 over epsilon times K points is sufficient and necessary. So this in particular, our upper bound improves a previous upper bound of Shamal, Kumar, and Vardarjan, which gave a bound of 1 over epsilon times K squared. And the connection to multiple LP regression is that basically you apply this Coreset construction once you find an optimal solution to this subspace approximation problem. So to conclude, we studied the problem of constructing Coresets for the multiple LP regression problem. And we gave a construction which has a nearly optimal size, which is in particular independent of the number of responses in the multiple LP regression problem. And as a result of our theorems, we give two applications. The first is a nearly optimal sublinear algorithm for Euclidean power means. And the second is a nearly optimal spanning Coreset for LP subspace approximation. And that's all the results that I had to share with you today. Thank you so much for your attention.